In this video, I'll explain to you how to collect gas over water. So collection of gas over water. So when do you use this? You use it like in a problem in which you want to collect the pressure of your gas, but you have water in the way. So let me show you a picture to see it better. So it will be something like this. You have your gas right here, but to collect it or to determine the pressure, you see that you have this water right here. So there'll be vapor getting inside with the gas. So it'll be kind of a mixture of your gas, in this case it's oxygen, and the vapor. So that makes it a problem when you want to collect only the pressure of the gas. And well, if you think about it, if it's a mixture, you will have to use the concept I talked about earlier, which is Dalton's law of partial pressures, which is, if you don't remember, stated pressure of the total is equal to the partial pressures of all gases. In this case, it will be the pressure of the water vapor plus the pressure of the oxygen. And this can be the pressure of any gas X. So whenever you have a problem in which you have to collect the pressure of the gas over water, you will simply have to add one more step, which is this step, this thing right here. So you will just want to, if you want the pressure of only your gas, you'll just solve for the gas in that equation. So in this case, pressure of oxygen will be pressure total minus the pressure of the water vapor. And then using the ideal gas law or anything, you can just solve for it. So solve for the pressure of the gas. Now I'll do a problem just to show you how it usually goes. So the problem says that we have 193 milliliters of oxygen gas. So they're giving us the volume of oxygen is 193 milliliters. And it was collected over water, so we have to apply the concept I talked about before. And the problem is also saying that the atmospheric pressure is about 762 millimeters of mercury. So the total pressure, you can think of it as the total pressure because it encompasses everything, is the atmosphere. It's 762 millimeters of mercury. And then it says the temperature of the water was 23 degrees Celsius. So temperature of H2O, 23 degrees Celsius. And the question is, how many grams of oxygen were collected? So the mass of oxygen gas. Now, the first thing I told you to do was, because it's collected over water, you want to apply this one up. Total pressure is equal to the pressure of the oxygen or the pressure of the water plus the pressure of the water. It doesn't, the order doesn't matter. It could be inverted. Now you may think, how will I get the pressure of the oxygen if we don't have the pressure of the water? However, whenever they give you the temperature of the water, you will also be given a chart that tells you what is the vapor pressure with that temperature. So it'll be something like this: temperature in degrees Celsius, pressure in millimeters of mercury. So when it's 23, it'll be something. When it's 24, it'll be something. When 25, it'll be something. Now, in this case, they don't give you the chart, but you can just look it up, and it's about 21.1 millimeters of mercury. So this is telling us that the pressure of H2O is 21.1 millimeters of mercury. So you just solve for the pressure of the oxygen, which is the gas you want. It would be the total pressure minus the pressure of the water. So it would be 762 millimeters of mercury minus 21.1 millimeters of mercury. So the pressure of our gas would be 740.9 millimeters of mercury. So that is the first step. Now we have the pressure of the gas, but they're asking us for the mass of the oxygen. So you'll want to use the ideal gas law, and we have the temperature, we have the pressure, we have the volume, and we always have the ideal gas constant, which is R. So you can determine the moles, and with the moles, just using the molar masses determine the mass. So let's do that. So our ideal gas law is PV equals nRT. But well, let's solve for number of moles first. PV over RT. However, I told you in the ideal gas law video that you will always want your pressure in atmospheres, your volume in liters, and your temperature in Kelvin, because then it wouldn't cancel out. If we were in that units, it wouldn't cancel out with the constant. So let's write our data here. This is 0.0821 liters atmospheres mole Kelvin. The temperature given was 23 degrees Celsius, which is 296.15. So that's done. Our volume was 193 milliliters. You just divide by 1,000 and you get 0.193 liters. That's done now. And finally we obtain the pressure of 740.9 millimeters of mercury, and that is equal to 0.974 atmospheres. It's just dividing 7 over 760 to get atmosphere. So now we have all the units, and plugging in all of the values here, I get 0.0077 moles of oxygen. So just to make it look better, you can say it's 7.7 times 10 to the minus 3 moles of oxygen. Now we have the number of moles, but we're not done. They ask for the mass. So you use the molar mass of oxygen. So it's just one more step. You have that 7.7, let's say 7.7 times 10 to the minus 3 moles of oxygen. Using our conversions, the molar mass of oxygen, the atomic, is 32 grams, about 32 grams. Sorry, this should go in the numerator, because as you remember, the denominator has the given unit, and we want it in grams, so 32 grams. So this moles will go with this moles, and just goes with the mass, and it's 0.24 grams of oxygen. And well, that's how you solve a problem in which you have your gas collected over water. Remember, the essential thing you have to do is subtract your vapor pressure to obtain from the total pressure to obtain your desired gas pressure, and then just normal stoichiometry.